Hi, this is Ash Venugopal, and you're watching another lesson in a series on data structures and algorithms. This one is on Quicksort, a popular sorting algorithm that is widely used in practice. In this first part, you'll see how the algorithm works and how to analyze its running time. In the second part, you'll learn how to write a Java program for Quicksort, including some fine-tuning techniques to make it more efficient. The input to the algorithm is an array of items. Quicksort will sort them without using any extra space, making it what's called an in-place sorting algorithm. Here's a big picture idea of what Quicksort does. Using the first item in the array as a pivot, it splits the array by rearranging the items so that everything that's less than the pivot appears to the left of it, and all other items, those that are greater than or equal to the pivot, appear to its right. The pivot is now in the correct place. If the left and right subarrays were to be sorted, then the entire array would be sorted. Quicksort proceeds to do exactly this by sorting the left and right subarrays recursively. This approach of splitting into parts, then recursively sorting the parts, is known as divide and conquer, and is used both by Quicksort and another sorting algorithm called merge sort, with remarkable speedups in running time. So how exactly does the split process rearrange the array items without using extra space and without the items stepping on each other's toes? It's actually a pretty simple yet clever approach, which we will now see with a few examples. Here's an extreme input situation to start with, in which the items are in reverse sorted order. The first item is the pivot. At the beginning, a left cursor is set to the second position, which is index 1, and a right cursor is set to the last position, which is index 6. The left cursor then starts advancing and keeps going as long as the item it is at is less than the pivot. Here, because all items are less than the pivot, the left cursor eventually runs off the end of the array, stopping when it hits the out-of-bounds index 7. At this point, all items in the array have been compared with the pivot, so the right cursor does not move at all. There's just one more thing to do. The item one spot before the left cursor, which is 1 at index 6, is swapped with the pivot 8. This brings all items less than 8 to its left. Since there are no items greater than or equal to 8, there is nothing to its right. The split process ends with the split point, the place where the pivot ends up, at index 6. This second example is another extreme case, and this time the input items are in sorted order. As before, the first item is the pivot, 1 in this case. The left cursor is set at index 1, and the right cursor is set at index 7. Recall that the left cursor will advance as long as its item is less than the pivot. Here, however, the left cursor item 2 is found to be not less than the pivot, and the cursor stops dead. Next, the right cursor starts moving backward, advancing as long as its item is not less than the pivot. This takes it all the way to item 3, at which point it advances one more step, which brings it to item 2, at the same spot as left. But since 2 has already been compared on behalf of the left cursor, a comparison is not done again, and the right cursor comes to a stop. All items in the array have been compared with the pivot, so we're ready to swap the pivot with the item that is one position before the left cursor. But here it happens to be the same as the pivot, so technically the pivot swaps with itself, which of course means we don't need to do anything. The split process ends with the split point at index 0. All other items fall to the right of the pivot. We have seen two extreme cases, a reverse sorted array and a sorted array. Here's a more general situation. With 7 as the pivot, the left cursor advances up to 8, and then the right cursor gets to 6. At this point, the left and right items are swapped, so that 6 is grouped with the other items that have been found to be less than the pivot, and 8 is grouped with those that have been found to be greater than or equal to the pivot. After the swap, the left and right cursors are advanced by one spot in their respective directions, in preparation for the next round of moves. But here, left and right cross over, which means they have both done their bit, and there are no more items in the array to compare against the pivot. This brings us to the last step, which is to swap the pivot with the item that is 1 before the left cursor. 7 swaps with 6, the split point is set to index 4, and the split process is all done. A final example to illustrate the split process. The pivot is 7 again. The left cursor moves up to 8 and stops since 8 is not less than the pivot. The right cursor moves down to 6 and stops since 6 is less than the pivot. 8 and 6 are swapped. The cursors step forward one spot in the respective directions, ready for the next go around. Continuing with the moves, the left cursor moves up to 9 and stops. All the items in the array have now been compared with the pivot, and it's time to swap the item one spot before the left cursor with the pivot. 5 and 7 trade places, the split point is set to index 4, and the split process is done. Now that we have a good understanding of split, let's apply it recursively to sort this input array. The first split breaks the array into items less than 15 and items not less than 15. Here's a quick run through of the split. The first recursion is on the left subarray with 14 as a pivot. This splits into 11, 12, and 13 to the left of 14 and nothing to its right. The next recursion is on the left subarray again with 11 as a pivot, which splits into 12 and 13 to the right of 11 and nothing to its left. The final split in this recursion sequence is on the right subarray with 12 as a pivot, which leaves 13 to its right and nothing to its left. The recursion sequence ends here since 13 is a singleton subarray. Backing up all the way to the result of the first split, recursion is now applied to the right subarray with 18 as the pivot, which puts 22 and 20 to its right and nothing to its left. The recursion continues with the right subarray with 22 as the pivot, which brings 20 to its left. The recursion sequence stops here since 20 is a singleton. Let's plug in the total number of item-to-item comparisons over all the splits. This is where Quicksort does all its work, and the count of comparisons is a proxy for the running time. In any split, all items except the pivot are compared against the pivot, so the number of comparisons is one less than the number of items in the array or subarray that is being split, which gives us these figures for our example. The total comes to 16 comparisons. Is this fast or slow? We saw early on that Quicksort uses a divide and conquer strategy to get speedups in the running time. But divide and conquer only works well if the divisions, that is the subarrays that result from a split, are evenly balanced in length. If the split is unbalanced, too many items will be on one side and too few on the other, which results in a lot more work to do in the conquering. You can see this in a previous extreme example of a sorted array. The splits are as lopsided as they can be, with every split pushing all items to the right of the pivot. The recursion tree that results is completely skewed, and the total number of comparisons over all the splits is the maximum possible, adding up to 28. In the other extreme, the best possible scenario is when the divisions are as even as possible. With a different arrangement of the same set of data values from 1 to 8 in the input, here's one best sequence of splits in the recursion tree. This consumes 7 comparisons in the first split, and 3 2 and 1 comparisons in the others, for a total of 13. This is less than half of the worst number, which was 28. It would be useful to generalize these results for best and worst scenarios. An example with 16 items shows how. Let's use n to stand for the number of items, so here n is 16. In the best scenario, splits will result in an even division. This picture is a little off from the actual because in the actual situation, an array of length 16 will split into 7 items to one side and 8 to the other, with the pivot in between. But to make the generalization easier, we'll go with 2 subarrays that are of length 8 each, and continue in the same vein, going all the way to the bottom of the recursion tree. The number of comparisons in the first split is taken to be 16, which is an overcount. We continue with the overcount using 8 for each split at the next level, then 4, and then 2. So on top of overestimating the subarray lengths, we're also overestimating the comparisons, but that's safer than undercounting. In any case, we're heading toward a big O figure, so being off by some constant will not make a difference. The total number of comparisons works out nicely if we consider going across each level, adding everything at that level. This gives 16 at the first, 16 at the second, twice 8, 16 again, 4 times 4, and 16 at the last level, 8 times 2. This adds up to 16 times 4. The overcounting we did works to our advantage because the multiplier 4 is the number of levels, which is log to the base 2 of 16, the array size. In other words, the number of comparisons is n times log to the base 2 of n. Contrast this with the worst case, where starting with the array of size 16, there would be 15 comparisons for the first split, which would skew everything to one side. This would result in 14 comparisons in the second split, 13 in the third, and so on. This gives us the arithmetic series from 1 to 15, which sums to 15 times 16 divided by 2, or 120. This generalizes to n minus 1 times n divided by 2. In summary, the worst case number of comparisons to quicksort an array of size n is n times n minus 1 divided by 2, which gives a running time of order n squared. And the best case number of comparisons is approximately n times log n to the base 2, for a running time of order n log n. If this was it, quicksort would not be a competitive sorting algorithm. After all, insertion sort's best case at order n beats quicksort's n log n, and its worst case at order n squared is no worse than quicksort's worst case. The reason quicksort is competitive and so widely used is that its average running time is order n log n. Insertion sort's average, by contrast, is worse at order n squared. Deriving the average running time for quicksort is beyond the scope of this lesson, so we'll take the order n log n figure for granted. Alright, we're done with the quicksort algorithm and running time analysis. In the second part, we'll see how to implement quicksort in Java, and also learn a couple of techniques to fine-tune its efficiency. See you then.